There is a word that gets thrown around constantly in any discussion of quantum computing, quantum physics, or quantum anything, really. It appears in textbooks, in news articles, in science documentaries, and in the mouths of people who are trying to sound knowledgeable at dinner parties. The word is superposition. And while it is one of the most genuinely important concepts in all of modern physics, it is also one of the most consistently misrepresented, oversimplified, and misused ideas in popular science. Today we are going to fix that. We are going to look carefully and honestly at what superposition actually is, what the mathematics behind it tells us, what it does not mean despite what you may have heard, and why it is the foundational idea that makes quantum computing not just faster, but categorically different from any computing that came before it. Let us start with the classical world, because that is the world our intuitions are built from. When you flip a coin and it lands on a table, it is heads or tails. It is not both. When a light switch is in the off position, no current flows. When it is on, current flows. At the scale of everyday life, things have definite states. They are here or there, up or down, on or off. This is so obvious and so universal in our experience that it barely seems worth stating. And yet it is exactly this assumption that things always have definite states, that quantum mechanics overturns at the smallest scales of nature. In quantum mechanics, a physical system, such as an electron, a photon, or an atom, does not necessarily have a definite value for its measurable properties before you measure them. An electron has a property called spin, which when measured along any given axis always gives one of two results: spin up or spin down. But before you measure it, the electron can exist in a state that is a combination of both spin up and spin down simultaneously. This combination is what we call a superposition. It is described mathematically by a wave function, which assigns a complex valued probability amplitude to each possible outcome. The square of the magnitude of those amplitudes gives you the probability of getting each result when you do measure. Before measurement, both possibilities are encoded in the wave function. After measurement, the wave function collapses to one definite outcome. Now here is the part where it is absolutely essential to be precise, because this is where popular accounts almost always go wrong in one of two directions. The first common mistake is to say that superposition just means we do not know which state the particle is in, that it is really in one definite state all along, and we are just ignorant of it. This is wrong, and it has been experimentally proven to be wrong. The experiments that test Bell's inequalities, which we discussed in our video on entanglement, have conclusively shown that quantum systems are not simply in hidden definite states that we have not discovered yet. The indefiniteness before measurement is a genuine feature of physical reality, not a reflection of our ignorance. The second common mistake goes in the opposite direction and says that because a particle is in superposition, it is literally in two places at once, or literally doing two things simultaneously, in some straightforward physical sense. This overclaims what the mathematics actually says, and leads to all sorts of confused thinking. Superposition is a property of the quantum state, the wave function, and what it tells us is that there is no fact of the matter about certain properties until a measurement is made. It is a statement about the structure of physical reality at the quantum level, and it does not map neatly onto our classical intuitions in either direction. With that foundation in place, let us talk about why superposition is so important for quantum computing. A classical computer bit is always 0 or 1, always, without exception. Every calculation a classical computer performs is built from sequences of definite zeros and ones being processed by logic gates. A qubit, the quantum equivalent, can exist in a superposition of 0 and 1. The quantum state of a qubit is described by two complex numbers called probability amplitudes, which encode the likelihood of measuring 0 or 1 and also contain phase information that plays a crucial role in quantum algorithms. When you have multiple qubits, the power of superposition compounds dramatically. Two qubits in superposition can collectively represent four states: 0, 0, 0, 1, 1, 0, and 1, 1 simultaneously. 3 qubits can represent 8 states. 10 qubits can represent 1,024 states. And this growth is exponential. 50 qubits in superposition can represent over 1 quadrillion states simultaneously. 300 qubits, as we have mentioned before, can represent more states than there are atoms in the observable universe. This exponential scaling is the source of quantum computing's theoretical power. But here is the critical caveat, and it is one that responsible science communication absolutely must include. Having a system that represents an exponentially large number of states simultaneously does not automatically mean you can extract exponentially more information from it. When you measure a quantum system in superposition, you get one outcome, a single definite result, chosen according to the probability amplitudes in the wave function. Measurement collapses the superposition. You do not get to read off all the states at once. This is why quantum algorithm design is so difficult and so mathematically sophisticated. The art of building a quantum algorithm is the art of using interference, the wave-like nature of quantum amplitudes, to arrange things so that the probability of measuring a wrong answer is suppressed, while the probability of measuring a correct answer is amplified before any measurement takes place. Superposition sets up the possibility. Interference harvests the result. Without both working together, superposition alone does not give you computational power. This is also why quantum computers are not simply better at everything. Superposition only provides an advantage when you can design an algorithm that cleverly uses interference to find the answer you want. For many problems, perhaps most problems, no such algorithm is known. And some theorists believe no such algorithm exists. The problems where quantum algorithms are known to provide provable speed-ups are real and important, but they form a specific subset of all computational problems, not a universal advantage. There is one more thing worth addressing, because it comes up constantly. Some people encountering superposition for the first time ask whether it means that consciousness or the act of human observation is what collapses the wave function. Whether the universe somehow depends on being looked at by a mind. This idea has a long and contentious history in the interpretation of quantum mechanics, and it was more seriously debated in the early days of the field. The overwhelming consensus among working physicists today is that observation in quantum mechanics means any physical interaction that entangles the measured system with a measuring apparatus or environment, not a conscious mind, not a human being looking, not awareness of any kind, a camera, a detector, a stray air molecule. Any of these can constitute a measurement in the quantum mechanical sense. Consciousness is not required, and introducing it creates far more problems than it solves. Superposition is strange. It is genuinely, profoundly strange. It tells us that reality at the quantum level does not work the way our everyday experience leads us to expect. But its strangeness is precise and mathematical, not mystical. And it is that precise mathematical strangeness that engineers and physicists are harnessing right now in laboratories around the world to build a new kind of computer, one that processes information according to rules that nature has been using since the beginning of the universe, rules that we are only now learning to control.